So, what will happen initially, and this is something I learned from collaborators usually, is you would start working on a project. And typically at the 1 or 2 month level, you understand, you start working on something new, you read papers, and after 1 or 2 or 3 months, you will realize whether there is this Goldilocks problem that exists in this particular direction or not. And a lot of times it is better to abandon something that doesn't seem to fall in the Goldilocks zone.
The guest of today's podcast is Dr. Chitraang Murdia. He is a theoretical physicist at UPenn Philadelphia, and his works comprise areas like CFTs, holography, and entanglement. So let's talk to Dr. Murdia about his work in physics and listen to what he has to say. Welcome to the podcast, Dr. Murdia. It's nice to have you.
Thank you for having me.
So before we talk about anything else, can you tell us a bit about the projects that you're working on nowadays?
Okay. So as you mentioned, there's a couple of different things that I work on. So one thing I'm working on currently is in the more quantum information line of things. The question that we're considering is a follow-up question of something we've looked at in the past, and that is how do we quantify multi-party entanglement, both in settings of like a multi-qubit system, but also in the context of a holography system. And if the various kinds of entanglement quantities we have can tell us something interesting about the entanglement you can have in a holographic setting. So just to give you a brief preview, like what we have sort of noticed is that certain kinds of entanglement patterns are upper bounded by other kinds of entanglement patterns. So you can derive some holographic inequalities that tell you that there are bounds on different types of entanglement, different types of multipartite entanglement in holography. That is one of the projects I'm working on right now. The other thing I'm working on is, or maybe two other things, related things I'm working on are continuations of older projects. And these are both in the domain of non-perturbative effects in the context of dualities between matrix models and two-dimensional superstring theories. So maybe we'll come back to that later and I can mention what I'm doing there.
Sure.
Because it's somewhat advanced and needs a bit of background.
Sure. Okay, so these are the main projects that you're working on. So before we talk about the different works that you have done in the past and the different kinds of works that you want to do in the future, let me ask you about your interest in physics. I mean, how did you get interested in physics? Because as is very well known that you appeared in JEE and you cleared your
Right.
JEE, you were the all India rank one,
Right.
but then you didn't do engineering and you went to
Yes.
do physics. So can you tell us a bit about the story about how you got interested into physics, and was there some book that made you interested in, or some person that you followed, and so on?
That's a great question. So, I mean, it's somewhat, it's sort of a long story, so maybe I'll sort of occupy some amount of time just talking about this. Uh, so, I mean, if for viewers who are familiar with JEE, the way JEE works is it's sort of an exam for people in towards the end of high school who go into college. And that exam basically comprises of sort of three subjects: math, physics, and chemistry. And so in preparation for that exam, most people will study these three subjects. And that is when sort of I started learning physics as like a proper subject, because until grade 10, like you sort of have sciences in general, but you sort of deal with everything very superficially. Uh, and then, so my high school physics teachers were extremely great, and they were sort of the first people who motivated me about physics. Before then, I was more of like a person who liked math better than physics. And it was mostly during high school that second sort of half of high school, that my sort of love and passion for physics started. And then also towards end of high school, I appeared in this contest or exam, which is known as International Physics Olympiad, where people from all across the globe sort of meet. And it's like a physics exam. There's like a 5-hour theory exam and a 5-hour experiment exam. And So participating in that sort of gave me a lens for what not really research looks like, but like sort of what problem solving, complicated problem solving in physics can look like. And that was really attractive to me. And then, J happened. I got sort of uh, my rank, and I started doing computer science at IIT. And even there in the first semester, we had a quantum mechanics course. Again, the professor was really great. So uh, I got back in touch with some other people who helped prepare me for my International Physics Olympiad exam. And sort of we together prepared a packet or a research packet that can sort of help me with a transfer admission. Because by then I was sort of set that computer science is not my calling and physics is the thing I want to do. And so after the end of my first year or first semester in IIT Bombay, I applied for a transfer admission and I heard back, I think, in May of that year. And after that, I moved to MIT to do physics. And then from then, it's sort of been more full time. Again, the professors at MIT, the professors at Berkeley have all been exceptional. So I think my love or sort of interest in physics is mainly due to all of the various teachers at high school, college, grad school that I've interacted with. Yeah,
So you said that before you realized that physics is your actual calling and not computer science. So you were doing computer science at IIT Bombay, right? So
that is correct.
were you really interested in computer science, or was it like a pressure to do computer science, as a lot of us feel in Indian subcontinent?
Yeah, that's sort of a bit of both, I guess. So you don't really know, right? Like until grade 12, you've never really studied computer science. You have no clue what it looks like. I've studied physics.
Hmm.
I know I like physics. Most people sort of with good ranks at IIT would choose a discipline like either computer science or electrical engineering. Those are where most of the good people go. And my initial thought process, part of it was, I'll start doing this. Maybe I like it. I've always liked math. Uh, and hopefully I'll make a career as a computer science academic. Once I got there, I realized that I absolutely hate coding. So computer science is not for me. And then from then, like the way to theoretical physics is basically be like, let me find the thing which lets me do most amount of work on pen and paper.
Hmm.
So it's somewhat negative reasoning that has led me here because I sort of love pen and paper calculations. Uh,
Hmm.
but yeah, initially it's some combination of pressure, a lack of knowledge, and also like a lack of resources, especially in India, if you want to pursue an education in pure sciences.
Hmm. I see. So, as you said that you like to do a lot of pen and paper calculations, as
Okay.
most theoretical physicists like.
Yeah.
So, should I take that as a hint that you don't use a lot of Mathematica in your research? Or do you use Mathematica?
Yeah, I mean, so
Mhm.
if you go talk to a computer scientist and tell them, like you use Mathematica to code, like they'll sort of laugh at you.
Yeah, I
So
know. All right.
yeah. So I think I do use a fair bit of Mathematica, but that's just like if you don't want to integrate things by hand, you'll use Mathematica.
Mhm.
So like small bits of plugging that you do there, or like to graph something or to make plots.
Sure.
I think that's like an extension of a pen and paper calculation for like most people. But there are hep theorists who would use more high powered like Python tools to do numerical simulations, stuff like that. I don't do any of that. So I just use Mathematica like as a symbolic calculator mostly.
So, what about when you have to do numerical analysis because the analytical solutions are just too hard to figure out because a lot
I
of people
find a
use Mathematica?
collaborator who's better at it than me. And I collaborate with them.
Sure, sure. That's clever, I would say. Okay. So okay, so you also said that when you were in IIT Bombay, you thought that okay, I should apply for a transfer admission because
Yes.
you realized that
Yeah.
physics is your actual calling. So how did that transition happen? So can I say that your teachers were the main reason why you realized that you like physics, or was there some other, influence on you? For example, some book or some other person on the internet, for example.
I would say it's mostly teachers. I mean, the books also probably contribute, but it's in my head, it's less direct in some sense as a contribution. I loved reading sort of, physics textbooks at various points, or yeah. So that was fascinating to me always. I can't think of a single book, that told me this is what I need to do. So it's mostly the teachers and this realization that maybe engineering is not for me. I would be someone who would like really enjoy doing something more physics focused. Uh, Mostly also as after a certain point it was just interest, right? Like you realize like you're taking a computer science course and you're taking a quantum mechanics course and you're enjoying the quantum mechanics course more than you're enjoying the computer science course. It's clear to you after a
Yes.
certain point, right, that you want to do physics. So I think it's more of that. Like when I put those two subjects in contrast with each other, it was clear to me that physics was winning out.
Right. And when you realized that you want to do physics, were you more specific? For example, did you know that you want to do high energy physics? Or did you say that, no, I just physics, whatever physics?
Initially, I mean, so most, again, people from South Asia might relate, like, we don't have much of an experimental background. Like, even when we
Hmm.
did our experiments for IFO, uh, we enjoyed the theory portion a lot. The experiments were, hard, and we were always struggling with them. And uh, so it was always theory in some sense. Uh, Later in my sort of education, when I started taking lab courses at MIT, it was clear that I was, uh, you know, struck with the theorist's curse, which means when I enter a lab, I'm going to break some equipment. The day you do that, you realize you're meant to be a theorist, right? Like it's the theorist's
Yeah.
curse.
I mean, but don't you think that experimentalists have also broken things in the lab because that happens?
Yeah, but then they want to fix it, and I didn't want to fix it. So, sort of, yeah.
Fair,
So what
fair
happened was we
enough.
were doing like an experiment involving liquid helium, I think. And there was some very expensive diode, and we just, snagged it. And there's usually like a little bit of ice that has formed. So the diode dropped into the vat of liquid helium. And then the lab staff was like appalled. They were like, this is a $2,000 device that you've dropped. And they were able to retrieve it eventually. Like they had to go fishing. So they made up some like makeshift hook and they fished it out. But it was clear to me like, okay, if you're yanking stuff, if you're not careful in the lab, you sort of don't have the patience for a lab person. You're sort of meant to be a theorist. So yeah, it was
Sure.
again sort of gradually clear to me that it had to be theory. And then high energy theory, again, the reasoning is sort of similar, right? Like in undergrad, I mostly worked on theoretical sort of QED for AMO physics, which was
Mhm.
fun, but again, a little bit too simulation heavy for me. So when I started grad school, I sort of made the conscious choice to migrate towards HEP theory, specifically like not phenomenology, but more theory in some sense, if people understand the difference. So I'm not doing the particle physics as in discovering new particle kind, doing the sort of string theory, uh, mathematical physics kind of theory, which is more, again, more theory heavy, less simulation heavy.
I see. So let's start talking about some of the work that you have done. So one, line of research that you have, worked in is CFT in the context of holography. So can
Mhm.
you tell us a bit about, I mean, for the audience mainly, that what is CFT and, why do we study it? What are the main reasons?
Yeah, so you probably had more informed guess about that who can tell a more historical perspective. So I'll sort of speak from a very limited, like my perspective lens on this, hopefully.
Hmm.
Uh, so at the very core, like the thing that makes life easy in physics is symmetry. If your system has a lot of symmetry, your life will be easier. And that sort of starts all the way from like high school physics when things like translational symmetry in time and space give you energy and momentum conservation. So we love symmetries because it makes like things nicer and easier and computable. And if we think about things at the level of quantum field theories, most quantum field theories have these standard symmetries, but CFTs are endowed with more symmetries, which makes them like extremely easy to work with in terms of computation. They're like extremely well behaved. And that is why initially, people were very interested in CFTs because the toolkit that you have in CFT sort of goes above and beyond the toolkit that people have in quantum field theories. And then in the 90s, people discovered this connection via holography between CFTs and certain kinds of gravitational setups, which are known as ADS universes. They discovered ADS CFT, And with that, we had the CFT methods to probe, let's call it, for lack of a better word, like quantum gravity. And that was sort of a revolution. And that's why I study CFT, because of this dictionary between ADS and CFT. So by using CFT tools, I am able to study quantum gravity, at least in this restrictive ADS setting.
I see. So when you have a particular CFT, you can deform CFTs by different ways, and you can study those deformations. So one deformation that you have worked on, and many people have worked on, is something
Mhm.
called the TTbar deformation. Can you explain a bit what that is, and why are people so interested in studying that deformation?
Okay, yes. So uh, so again, there's the deformation, what it does to the CFT, and then how we think it acts on the ADS. And I'm going to sort of start with the CFT and then move on to the ADS and explain why it's an interesting thing to do. So on the CFT, all you're doing is when you have the CFT action, you deform it by this TTbar thing, as you know. Here, T stands for sort of the stress tensor. So in the case of 2D CFTs, you have a T, which is like if you work in holomorphic coordinates, uh, you just have a T, which is sort of the holomorphic guy, and then you have a T bar, which is the anti-holomorphic guy. So TT bar is basically like if you take the stress tensor and then you do T mu nu, T mu nu with upper and lower indices, you get this TT bar object, which in the holomorphic coordinate sort of looks like TT bar minus something. So you deform the CFT step by step by this operator, and you get a deformed CFT, which is known as this TT bar deformed CFT. It is interesting because on the CFT side, you can sort of, do a calculation sort of step by step by step. But the main power comes from the fact that on the ADS side, what this is doing is it's pulling sort of the radial cutoff deeper and deeper into the bulk.
Right.
So, yeah, go ahead.
No, sorry. Please go on. I was just saying right.
Uh, And what that enables you to do is, all the things that you could have done by attaching them at the asymptotic boundary, for people who don't understand the sort of the boundary at infinity, you can now start doing a lot of those things at a boundary that lives way deeper inside the bulk at some fixed value of R, depending on how much you've deformed the CFT by this TT bar operator.
Mhm.
So it is this radial sort of cutoff moving inwards that gives TT bar a lot of its power. Because whatever toolkit I had in the ordinary ADS CFT, I now have in this new paradigm, and I can start probing the interior a bit better. And people have sort of taken this further. So I worked on this maybe like 7, 8 years ago. People have taken this a lot further now, and they do like all sorts of cool things with it. They slice the ADS can be sort of completely sliced in this way using a TT bar deformation, like you can run it all the way to the sort of center of the bulk. And yeah, that's partly why it's interesting is because it is a new member of a dictionary instead of just the standard duality between ADS and CFT. You now have this duality between a radially cut off ADS and a TT bar deformed CFT.
Right. So if I'm not wrong, I think your first paper was about TT bar deformations, right?
Yes.
And in that paper, you studied TT bar deformations, and you also related that to Ryota-Yanagi formula. So can
Yes.
you tell us a bit about what that formula is and what was the calculation? What were the calculations that you did in that paper?
Good. Okay, so I'll start with the RT formula first. Again, I've talked about this ADS CFT duality, but one of the best places to see this duality actually in action is this formula, which was discovered, I think, in 2006. It's called the Ryota-Yanagi formula. And what this formula is trying to compute is on the CFT. So for now, let's imagine that the CFT sort of lives on a circle, which goes up in time. And I want to find the entanglement entropy of some interval on the circle. So that's a purely CFT quantity, right? There are pure CFT methods people can use to do this computation. If I now believe in this ADS CFT dictionary, then I can ask a question of what in the holographic context computes for me the entanglement entropy of an interval. That quantity is given by the smallest area surface, which is what we call the geodesic, that sort of lives in the ADS spacetime. So you start on the boundary of the interval, and then you find the smallest, in this case, length surface that connects those two endpoints. And the length of that geodesic surface is proportional to the entanglement entropy. And you can fix the proportionality constant eventually, and that is the RT formula. So
Right. Okay.
this is the basic RT formula. There are like advanced versions of it. There's the Hubeni-Rangamani-Tagyanagi formula, which sort of takes this basic idea and takes it into what happens if you have like a time evolving space-time. So, and then you can also sort of add quantum corrections to this, and you get the Engelhardt-Wall prescription. But at the very core, it's asking this question of what in the ADS context computes the entanglement entropy of boundary interval. Okay, so far we've played this game on the asymptotic sort of setup, and now I can start doing these matches with the TTbar deformed example, right? So there again, you can do this TTbar deformation, figure out what the entanglement entropy looks like, and then ask the question of what is the correct prescription, or what is the correct modification of the RT formula that gives you the same answer. And then in that case, it happens to be, you have to do this radial cutoff. And again, with the new radial cutoffs, you're not living at the asymptotic boundary, but at some other boundary. And then you again find the minimal surface that computes for you the entanglement entropy. So it was sort of a match between these two quantities. I think someone before us had done it for the 2D case. We generalized it to higher dimensions. And part of the issues there were, dealing with some of the terms that sit on the boundary, because your boundary is no longer asymptotic, sort of moved in. So there were some correction terms you had to add, and you had to be a bit careful. So it was a very sort of short paper in some sense, but it had this very clean result of this match being true if you were careful about all the pieces that had to be accounted for.
Right. So you said that, for example, when you gave the example of the circle, that CFT lives on the circle, you
Yeah.
can have an interval and talk about the entanglement entropy,
Yeah.
and then find the extremal surface. So for a given interval, is it true that the extremal surface is unique, or can there be more than one extremal surfaces with the same length?
Typically, you would just have a unique extremal surface. So extremal means you just extremize locally. So you could have multiple extremal surfaces, and in that case, you would choose the one with the minimum area if you have multiple candidates. And
Right.
if you have two candidates that have the same area, like same minimum area, then the answer is obvious, right? If there are two, you sort of get the same answer. Uh, but typically that's very like you really need to engineer a space-time that really has this property. So in this very basic example, it's unique. If you just start with like vacuum ADS, the like if people have taken like a GR course or something, uh, they might have already computed it. So if you work in this upper half plane picture, the geodesics are just given by semicircles. So it's unique in that sense. With more complicated spacetimes, you can engineer configurations where it's not unique, but the prescription then also tells you what to do. So typically unique, you can run into corner cases where it's not.
I see. So another line of research, I mean, which is a bit related to this, I mean, didn't include TTbar deformation, if I'm not wrong, but
Mhm.
that was more recent with, Andreas Karch, for example. It was
Mhm.
about interface CFTs, and
Yes.
you, did this work where you try to write down the, boundary entropy function for entropy CFTs. And I think there too, you are talking about the entanglement entropy of an interval. So
That's right.
can you tell us a bit about that project?
Uh, right. So I guess I'll sort of talk about simultaneously about two different projects in this direction. So one of them was this later paper with Andreas and Evangelos, and then there's an earlier work with Raghu Mahajan and Irit
Yes.
Krutov, which does a version of that computation, but in the very specific setting of free fermion CFTs. And both of them are asking this question. So, okay, so initially you just think of some simple CFT. You have an interval, you compute the entanglement entropy. Now I can have more interesting looking CFTs. One of them is called the boundary conformal field theory, where instead of having a CFT that lives on the entire line, you just have this live on a half line. So you have a boundary, let's say at x equals 0, where the space-time terminates. And then you keep asking the same questions of what is the entanglement entropy of an interval in this setting. And then the setting that we probed was the setting of an ICFT, where you take two of these BCFTs, one living on the plus half space, the other living on the negative half space, and you couple them at the origin so that you can have some amount of, like, let's say, some transport, some reflection transmission going on at the interface. If you make that reflection sort of if you make it completely reflective, you get two decoupled boundary conformal field theories. If you make this interface completely transmissive, you just get a single CFT. However, in the interregime, when it's not purely reflective and not purely transmissive, uh, the question then becomes, can you tell me what the entanglement entropy of an interval looks like? It could be an interval that straddles across the defect, or it could be just an interval that lives on one side, which will sort of see the effects of the defect because it's there somewhere, like living in my space-time. And so both of these projects were interested in the question of computing this entanglement entropy in the specific context, again, of 2D CFTs. The first one we were interested because we wanted to push some early results and say that they hold in settings where transmission reflection is allowed. So there we were just trying to compute the entanglement entropy of an interval that goes across the defect. And the simplest setting we found for that was this free fermion CFT. And after using sort of techniques that were developed by people in earlier works like Cassini and Huerta and other people, we were able to sort of push the barrier for what was known and figure out what the entanglement entropy looks like for a free fermion CFT in the sort of interval that straddles the defect. And then this later work came because, Andreas was giving a talk at Penn and we sort of got chatting. And the idea there was not in the specific context, but in the general context of any interacting conformal field theory, can we at least, you will not have a general answer, but you can have a form for an answer. And then based on inequalities that the ICFT entanglement entropy needs to satisfy, things like, strong subadditivity. It's a well-known inequality for entanglement entropy. Can you say something interesting about the entanglement entropy? And you can then start bounding things and you can at least arrive at certain interesting results about inequalities for the entanglement entropy. And that was sort of the nature of this last project, uh, where we found an interesting inequality. We checked it in two settings: the free fermion CFT, a holographic CFT, and I think they recently had another paper sort of pushing this envelope further, like Evangelos and Andreas, I think, have had a paper yesterday or day before that was pushing this envelope further. But the core idea is just starting from very basic things about the CFT entanglement entropy. Can you learn anything about the ICFT entanglement entropy?
I see. So, if I'm not wrong, I think when you were at UC Berkeley, you were in a Rafael Busso's group.
I was in Yasunori Nomura's group actually, but sort of,
Okay.
yeah.
But you did interact with
Yeah,
his group, and
of
right,
course.
and his group is like a big proponent of this approach to solving the black hole information paradox called the island approach.
Yeah,
And
yes,
you also have some papers on entanglement islands. So
yes.
can you tell us a bit about what that whole approach is and what are entanglement islands?
Yes. Uh, so, uh, in terms of context, This is trying to solve this black hole information puzzle, which is asking the question of what happens to the information inside a black hole, like as it evaporates. So the solution as we believe it now comes in the form of entanglement islands. Uh, so the initial approach as developed by sort of a bunch of people, Pennington and then Almahiri, Engelhardt, Merolf, and Maxfield, I think in 2019, they found a resolution to this problem. And the resolution looks like, uh, as you were talking about earlier, there's this RT formula, and then there are, you know, generalizations. So you now consider this generalization that also takes into account uh, so there is for the entanglement entropy, there's a part that comes from the RT formula, which looks like the area. But then there's also sort of bulk entanglement entropy that comes from the bulk quantum fields that live in your spacetime. So suppose you have an electron inside the black hole and an electron outside the black hole that are entangled with each other. If I then ask you a question of how much entanglement entropy the black hole has, of course there will be a contribution that comes from this entanglement between the two electrons that are sort of one inside, one outside. Uh, so once you include these corrections, in the black hole context, what you realize is that after the page time, which is roughly when half of the black hole has evaporated, what you find out is that in addition to the standard RT surface that lives at the origin, roughly speaking, you get an additional RT surface uh, that lives a little bit inside the black hole horizon. This is surprising because this surface is not close to any classically extremal surface. The classically extremal surface is still sort of at the origin. However, this is a valid extremal surface when you include the corrections from the quantum fields. Typically, those corrections are what we think of as subleading in some sort of Taylor series approximation. So these are typically the first subleading corrections. And typically, like most of us are familiar with some kind of Taylor series approach where the corrections only change things by a little bit. However, in this context, these first subleading corrections become extremely large. They become large enough to compete with the leading order term. And this is what precisely stabilizes uh, the this new quantum extremal surface, which is known as the island. So now if I ask you a question of what does the uh, entanglement entropy, like what is the extremal surface that computes for me the entanglement entropy of a radiation bath, which is where I'm collecting sort of all the things that radiate out of a black hole. Initially, I will find that uh, the QES sort of lives at the origin, but after page time, I get this island extremal surface, which is telling me that the radiation is entangled with things inside the black hole. So I can now use the radiation to diagnose things inside the black hole. So the information has leaked out because now entanglement has been created, right? So initially what was not entangled or which didn't appear so entangled is now heavily entangled. And this is the way in which the radiation sort of has captured information inside the black hole. The information has leaked out. And that's a sort of resolution, or at least partial resolution towards the Hawking information paradox.
I see. So it may be, I'm asking this question because someone who is vaguely familiar with, black hole information paradox and
Mhm.
attempts to solve this particular paradox may ask. So are you familiar with this theorem called the small corrections theorem by Samir Madar?
I think so. But can you
Yeah.
remind me again if
So I think effectively what it says is that you cannot solve the black hole information paradox by small extra corrections, small corrections, right?
Mhm.
So some student may ask that, so you are saying that these extra corrections, they are very important. So how does it square with that theorem? So how would you say?
So yeah, I would sort of plead a little bit of ignorance. I'm not familiar how the proof works because, as I said, like these corrections naively appear small, but now they're no longer small, right? They're like actually as
Hmm.
large as the leading order term. So I'm not even sure if this is like satisfies the axioms of the theorem anymore. I'm sort of not exactly familiar with the axioms say, and is this a small correction anymore? My first hunch would be to sort of use that line of defense, right? This is no longer a small correction. It is as large as the leading correction. Uh, so
I see. That's why.
yeah,
But if that's the case, someone can ask that, okay, why stop there? I mean, are there other corrections that are as large as the leading order that we are missing? So do you think that's the case, or do you think that no, we are including all the big corrections now?
I think we're including all the big corrections. Uh, this is like this is again a somewhat engineered setting, so maybe more generally you would expect the corrections to really come from some sort of graviton entanglement. This entanglement is usually put some external field on top, and then that is the quantum sort of correction that corrects things. So maybe there are other pieces that are potentially equally large, which we have not found ways to properly diagnose. And those might sort of, again, change the sort of minute details of the resolution, or they might resolve the paradox in more general settings. But right now, I think in this particular setting, we at least have one channel by which the leak occurs, and that leak sort of takes the information out. You could have other corrections that might lead to other channels that cause this kind of leakage of information. So if those are present, those will only strengthen the resolution.
I see. I see. Okay, so in the last, I would say almost 10 years or probably more, I think, because it started from 2014, I would say. So in the last decade, I would say, there has been a lot of work done on generalized symmetries and non-invertible symmetries and things like that, where symmetries are seen as topological operators, right? So
Mhm,
there is this work that you did with Jonathan Heckman and some collaborators where you try to find the holographic dual of a topological symmetry operator, and you came to this conclusion that global symmetries may
mhm,
not exist for asymptotically area spacetimes for
mhm,
p greater than or equal to zero, where p is the number that tells you what is the how
mhm,
the symmetry is, right? So can you tell us a bit about that project, and how did you, I mean, if it is easy to describe in words, and using some jargon, that how did you come to this conclusion that there can't be any global symmetries for asymptotically area spacetimes?
mhm. So again, the conclusion that no global symmetries exist was sort of well known anecdotally and even at the level of papers before we worked on this. There's a proof by Harlow and Oguri that
Mm-hmm.
independently proves uh, no global symmetries. There are proofs that sort of reference something called remanence that one can use to say that there are no global symmetries. So this idea of no global symmetries is a part of the folklore and even theoretical literature for a long time. We were interested in coming up with a more modern proof that uses some of these things that you mentioned, these topological operators, so it would be sort of more general because it would not just say no global symmetries of the ordinary like zero form kind as we know and love, but there are some things called higher form symmetries, uh, which might be a bit hard to explain, but there's like a whole plethora of symmetries that arise. And we wanted an argument that sort of rules all of these kinds of global symmetries in sort of one shot. So that was the motivation behind the project. In terms of the proof strategy, the basic key philosophical idea is that there is a fundamental sort of contradiction between having a global symmetry, which leads to these things called topological operators. So every global symmetry comes with a topological operator. And what this topological operator does is that it can link with the charge. So in the case of an ordinary sort of setup, uh, the charged objects can link with topological operators. So in sort of a 3D setting, if your charged object is basically a loop, your topological operator is a different loop that can link with it. And then when you try to unlink them, this topological operator will act upon the charged object. That is the key modern formulation of global symmetries. And the good thing about this formulation is that it not only lets you handle these sort of basic zero form symmetries like charge conservation, but it also lets you handle these higher form symmetries because it's all a statement of linking. So for example, in this three-dimensional setting, one-dimensional things can link with one-dimensional things, zero-dimensional things can link with two-dimensional things, and two-dimensional things can link with zero-dimensional things. So there's already three different kinds of symmetries that are working together here. So on the one side, you assume you have a global symmetry which tells you that there's a topological operator. If it's topological, you can deform it without any cost. So I can make it as large or as small as I like. There is no cost to that because there is no term in the action which sort of penalizes my deformations. And this is fundamentally in contradiction with ideas from ADS CFT, this idea of subregion duality, which tells you that uh, a certain subregion on the boundary can only probe so much of the bulk. So if I have this topological operator, roughly speaking, what I'm allowed to do is I can make it as large as I like. So it will fundamentally break this subregion duality. So if I believe in subregion duality, which we have now like a large reason to believe in, it immediately tells me that a topological operator is not allowed. If it's not
Right.
allowed, it has to be non-topological. And if there are no topological operators, there's no global symmetries.
There's no global.
So
So when you say subregion duality, I mean, can we also say that a connected subregion on the boundary can only probe a connected subregion of the bulk, or can it be disconnected?
uh, I mean, so there is versions of it, I guess, which is why I'm taking a little bit of time to answer your question, right? So you could
Hmm.
think of like a subregion that looks like two intervals. That's a
Hmm.
disconnected subregion. In
Yes.
that case, you could get uh, the subregions you get if these intervals sit very far, you'll just get two different disconnected subregions, right? Because they'll not interact with each other. However, if
Sure.
you put them really close, it is possible that they probe but much deeper, and you'll get like a bridge or a tunnel that connects these two guys. So both
Right.
possibilities are allowed depending on the configuration. So
See.
yeah, but
And
but for the purposes of our proof, we just use a very simple case of a single interval or like a single region. In general, subregion duality sort of extends to single intervals, multiple intervals, many different things. And depending on how the geometry is arranged, the solution in the bulk can look connected, disconnected. Yeah,
right. And you also generalize those results to theories which are not even CFTs, which are quantum field theories. And I think they're the conclusion was that you cannot have global symmetries for minus m, where m was greater than or equal to minus 2, right? So
right.
how do you make sense? I mean, this is something that people have worked on, but for the audience who may be who may be familiar with global symmetries but are not familiar with like minus one form symmetries, because how do you even make sense of minus one form or minus two form symmetries? So can you tell us a bit about how to make sense of these kind of symmetries?
Right. Okay, so minus one is a little bit easier because minus one is just denoting the fact that you have some parameters in your theory. That is
Hmm.
what minus one from like loosely means. There's just some parameter in your theory, and there like what a symmetry change looks like is you have some domain wall that sits in the deep bulk. So
Hmm.
minus one form is a little bit easy to reconcile with because we always have free parameters in our theory, right? Uh, Minus two is a little bit of a stretch, and what we wanted to get at here was that the way that argument works is minus two in QFT implies some, say, zero or one or two form in some other sort of lower dimensional CFT that lives within the QFT. So it's not a direct contradiction, it is this indirect contradiction that works this way. Uh, So for me, it is also still very hard to visualize what like a minus five form symmetry looks like. What I can visualize is that minus five will imply some zero forms for some intermediate CFT that I can
Yes.
have in my QFT bulk. And there, things are maybe a bit easier to visualize. So it's basically by using some kind of uplift and downlift arguments that
Right, right.
things can be made to work.
I see. That makes sense. So, some months ago, I would say, well, almost a year, sorry, half a year ago, I, talked to Raghu Mahajan, and he was talking about, his efforts to understand the non-perturbative definition of string theory, and because of that, he's working on these, simple models like minimal string theory, Liouville theory, and things like that. And you have some papers with him in this particular
Yes.
quest. So, can you tell us a bit about what is like minimal string theory and matrix models that are used to understand them, and how does that help you in understanding the non-perturbative definition of string theory even in the long run? I mean, probably not in the short run, but in the long run.
Yes. Okay, so I think there's a lot of questions there, so I'll sort of unpack them one by one by one.
Sure.
I think I'll answer the broadest question first, which is why care about this line of research? The simple answer is, uh, again, as physicists, especially as theoretical physicists, we love simplifying assumptions. Like, give me a model that is computable, and that is any day better than a more physical model that is not computable. So, there's the classic example of spherical cows, if people have heard about it. Like, somebody was asked to do some computation with cows, and they just assumed that the cows are spherical objects because that makes life easier. So why deal with non-perturbative corrections in two-dimensional string theories? Because it's very simple. The matrix model is an extremely simple theory, and the 2D string theory is also not that complicated. It doesn't have all of the issues that you run into when you're doing like full 10-dimensional superstring theories, for example. So that's why this is an interesting quest, because anything that you need to finally understand in the 10-dimensional setting, you can have a baby example in this 2D setting where everything is very nice to compute. I can take it to the sort of last point, so on and so forth. And that is why uh, this is an interesting quest, because non-perturbative corrections are extremely difficult to study. And so it is very easy to develop the whole toolkit first in this restrictive 2D setting. Check that the toolkit is working by utilizing the matrix model duality, and then push these tools further to the 10-dimensional setting. And that's what people have already done in certain cases. There are calculations by like Ashok Sen and other people where they've pushed some of these computations into the 10D superstring theory setting already. That is why this is an interesting quest, because it's very computable, and it's very easy to figure out where there are flaws, where you need assumptions, where you need to sort of fix plugs. That sort of hopefully answers why this is an interesting aspect.
Mhm.
Uh, the next question, I think, is about what these two theories are. So the matrix model, or I should say like what we work is even simpler. It's not even a model, it's just a matrix integral. It's just an integral over matrices. You just start with some n by n matrix. You do an integral which looks like an integral dm, and then you put a term that looks like trace of some polynomial of the matrix in an exponential. That sort of serves as your action term in some sense. Uh, and then you do an integral over all matrices, and you choose some appropriate measure that has all the symmetries. Like if you're integrating over Hermitian or you're integrating over unitary matrices, you choose some appropriate Haar measure. So that one looks really simple, right? Like the one by one matrix example would just be a one-dimensional integral, like the ordinary thing we sort of know and love from high school. Uh, Even this sort of matrix setting is not that difficult. It's an integral over, like if it's an n by n matrix, it's just an integral over n square variables. Looks very simple in some sense. And then people over the years have developed techniques that makes this sort of much easier. Uh, So that is what the matrix integral is. The matrix model is sort of you sort of push all of this to the level of some sort of quantum mechanical model, then you get something called the matrix model. But we usually work with the more simple matrix integrals. So on the matrix side, life is very easy to compute. You start with the n by n matrix, you do some operations, you do an integral, and then to get the thing that is dual to the string theory, you just take what is called a double scaling limit. What that means is you send the size of the matrix to infinity, and simultaneously you tune some of the couplings in this polynomial uh, to get something that is going to eventually be dual uh, to your string theory. So you can imagine it's just some simple integral followed by some simple limits. And we have a lot of theoretical toolkits here that make this whole quest sort of fairly easy. There, the non-perturbative contributions, okay, what do those guys look like? So let's imagine I have because the matrix is size n by n, I have n eigenvalues. And it's typically in the eigenvalue sort of, I represent the matrix in terms of its eigenvalues and then some u and u dagger that diagonalize the matrix. That is typically the choice of variables we like working with. And you can integrate out this u and u dagger matrix to get an integral that purely integrates over the n eigenvalues. So the matrix integral simplifies to an integral over n eigenvalues. And in the large n limit, what it looks like is that the eigenvalues sort of condense into a droplet and occupy some minimum of the potential. Now, what non-perturbative contributions look like here is I take one of these eigenvalues away from the droplet and put it at some other extrema of the potential. That is what a non-perturbative contribution looks like. You can check this. If you look at what the actions look like, what's the difference of the action? It's basically n times the difference between sort of the potential where the droplet lives and where you put this new eigenvalue. So it looks like e to the minus n times some number. And for large n, this is non-perturbative because, again, as people might be familiar, e to the minus large number is non-perturbative. It's not something I can expand in powers of 1 over n. Like if you're familiar, e to the minus 1 over x goes to 0, doesn't have a Taylor series expansion. And that's the sense in which this is non-perturbative. Okay. So that's what the non-perturbative corrections look like in the matrix model. So it's very simple thing. You move the eigenvalues around, gives you pretty much the non-perturbative corrections on the nose. There's a couple of bookkeeping factors that you need to take into account. But those are just some kind of saddle point approximation. So again, you can do them sort of fairly easily. That takes care of the matrix model side of things. So hopefully I've explained what the matrix model is and what the non-perturbative corrections look like. This all sounds very easy. It actually also is very easy. And so usually when we're working on any of these projects, the matrix model usually gets done first, and it happens over the course of a week. Okay, now let's go to string theory.
Sure.
What is minimal string theory? So why care? We care because it's dual to these matrix models where, as I said, the computations are fairly easy, but it is still a full-blown string theory. So it's interesting. Minimal string theory consists of 3 different pieces. At the level of the string theory, even if you have a superstring, you sort of just put super in front of every word and you're done. So minimal string theory has 3 different pieces, and I'm not sure if the words are familiar, but there's the first piece is called the Liouville theory. It is some standard scalar field theory with some little bit of correction terms. The second thing is called a minimal model. That's also a very well-known CFT that we've sort of, again, have a lot of literature on. And the third piece is this sort of BC ghost piece, which is sort of, again, if you've taken a string theory course, you're probably familiar with BC ghost. It's one of the first things you learn. So you take these 3 pieces, you put them together, and you get minimal string theory.
And you need 3 pieces because you want the whole central charge to be 0, right?
That is correct. That is correct.
Right.
So yeah,
And when you say minimal model, can you take any minimal model because there are like infinity of them?
Yes. So again, the central charge of the minimal model depends on the choice of the minimal model.
Yes.
That central charge sort of precisely needs to match with the central charge of the Liouville so that the total guy vanishes, because the BC ghost will always give you like a minus 26.
Minus 26. And the minimal model, does that have to be unitary?
No, it does not have to be unitary. So you can choose the non-unitary members. Typically, so again, depending on the kind of matrix models you have, there are different families. So if you choose like a 2, p minimal model, that will give you a 1 matrix model, which is the kind I've described so far. But you can start with a p, q minimal model. Again, you need p and q to be co-prime to sort of have something nice. Those are, again, typically non-unitary. But even for P comma Q, you can choose an appropriate Liouville, put the BC ghosts, get your string theory, and then instead of a one matrix model, you now have a two matrix model. But there's a duality there again.
Right.
Yeah,
So
you
when
can
you say,
typically choose. Sorry, go ahead.
so sorry, when you say that choose an appropriate Liouville, what do you mean by that? Because so if I'm not wrong, in Liouville theory, the central charge depends on this thing called Q, which in turn depends on B. So is that what you mean? Choose an
Exactly,
appropriate B.
exactly. Just choose the B appropriately. So square root
Okay.
P over Q for a
Yes.
PQ minimal model.
I see. I
Yeah,
see.
yeah. So you just choose that B so that the total central charge vanishes. But the good thing is, except for this relationship that relates uh, PQ to B, these three sectors like some are completely independent, right? There's no coupling term between them. There's no explicit coupling. So if I need to compute any physical quantity, I can just multiply the three answers, roughly speaking, together. I can multiply the Liouville times minimal model times BC ghost. That's my full answer. That is the
Okay.
power because there's no coupling. These three things are independent of each other. The only coupling is through this central charge relationship. Uh, if I have a good enough sort of table of quantities in these three theories, which we now do, computations become simple. So
Okay.
uh, I can sort of get into the complications of the computation in a bit, but the basic idea is that, yes, you just have these three pieces, you put them together, and then you try to start computing non-perturbative contributions now, which come from like certain kinds of instantons or branes. In this case, they're called the ZZ instantons. Uh, and then there you can again do a computation. And what we found, and have now extended it to like, again, various generalizations, is that there is an exact match. And by exact, I mean the coefficients, like the numerical coefficients up to like factors of 2 and pi match up between the matrix model and this minimal string theory.
Right. So when you were doing these, when you're trying to get these matches, correct me if I'm wrong, but there was this problem where you have these divergences where you
Yes.
have, Z, instantons on, on two Z instantons. So you have an analyst, right? And
Yes.
you had to use string field theory to, resolve them. So where did string field theory come in all of this?
Good. Yeah, so I think that's what's the string field theory and curing of the divergences is what makes these projects interesting, because that's really where the hard part of the calculations, like so far, whatever I've described for you is like putting a bunch of pieces together, doing a bunch of computations, and most things work out barring this like little bit of divergence factor, which is where the main like computational difficulty and the sort of full-blown math comes in. Uh, so uh, maybe just to make this problem a little bit more like stark, let me start by giving a bit of context. Okay, so initially I said that there was this large N in the matrix model, right? Uh, what this corresponds to is a 1 over GS, where GS is what we call the string coupling. So that is the small parameter in string theory. So large N is the same as small GS, and they are related by some inverse relationship. So if I'm working with the matrix model, uh, if I expand something about its extrema and then do a Gaussian integral, if that term looks like n times some function f of x, doing a saddle point approximation gives me something that looks like 1 over square root of n times f double prime. Uh, Maybe I said those words too quickly, but this is sort of how the standard saddle point approximation works. So you get
I
one.
can include an equation when I'm editing this so that it will help you.
Okay. Okay, perfect. So you get a 1 over square root n type of correction that multiplies these non-perturbative effects. That looks like a square root GS type correction. And typically, all of the things you've been evaluating so far will, on the string theory side, look like e to some series of GS, some Taylor or some Maclaurin series of GS. So how does a e to the polynomial produce for you a square root GS, which looks like this polynomial has a log GS correction? Naively, that seems pretty much impossible. That is what string field theory comes in plugs for you, because when you start computing the cylinder, you get some divergence. So initially the cylinder looks like it doesn't see GS at all. There's no initial GSs in the cylinder. It just looks like it's going to turn out to be a number. The first surprise is that this number looks like it's going to blow up. And then when you include string field theory corrections, the blow up gets regulated because you get a log GS. That is very surprising because you were not even expecting, like if you think about standard genus counting type arguments which we use in string theory, the cylinder is going to give you a GS to the power 0.
Yeah.
That turns out to be a log GS indeed. That is the surprise. That is
I
what
mean,
helps you cure everything. Go
if you
ahead.
think about it, it could if log G was gonna come, it couldn't be anything else but G power 0, because if it was G power something else,
Correct.
that would be surprising.
No, I agree with the other way around. Like log GS is something that looks like G power 0. But
Yeah,
G
yeah,
power
sure.
0 looks like log GS, and you get it from a calculation that initially has no log GSs. Initially, if you set up the computation, you just get integral over number times number, like something like that, roughly speaking. There's no GS factors when you set up the cylinder initially.
Yeah, I agree. So that's
Okay,
where string field theory came into. Okay.
so that's where string field theory comes in. To go into a little bit more detail, what's happening is when you're evaluating the cylinder diagram and you work in the open string channel, which means that there's only one modulus on what parameter of the cylinder, which is the ratio of its height to its circumference. That is your one parameterization of a cylinder. So if you make that parameter sort of super large, I will get a cylinder that is very like long in circumference, but very sort of narrow. So I get like a ribbon, sort of speaking.
Mhm.
If I make that parameter very small, I get a very like narrow pipe. So if I'm making the parameter large, I'm getting this ribbon. And the divergence lives in this limit of parameter space or moduli space.
Mhm.
Uh, so it is a long range divergence here. It is what you will call an infrared divergence. And we know that that is typically the kind of divergence that string field theory comes and cures for us. So this is coming because you have modes that are either tachyonic, which means they have negative sort of mass, or zero modes, which means they have sort of zero mass. Those modes propagate and don't decay or die out in the ways that massive modes die out in the IR. So those modes initially look like a divergence, and that is what you cure using string field theory here. You cure the IR divergences coming from the tachyons and coming from the zero modes.
I see. So when you said that the branes in the minimal string theory are ZZ branes because they are the boundary conditions or the boundary states in Liouville
Yes,
theory,
yes.
we also have FZZT. So don't you use that in your work, or do you use that as well?
Uh, so the FZZTs don't give you the kind of non-perturbative, like instantonic corrections that we're
I
looking
see.
for.
Hmm.
So we usually like don't have, barring like one or two projects where like we were interested in the FZZT boundary conditions, is typically the ZZ that give you your instantons because again, uh, those are the saddle points, so as to speak, that are separated in their action from like the zero or the vacuum. So we usually are only using the ZZ boundary conditions in most of our projects.
Right. So in this line of research, do you have some more projects planned for the future?
Yes, so as I mentioned towards the beginning of the podcast, I do have two different projects I'm working on currently. Uh, the first one is uh, pushing again these techniques to one particular model now. So it's a superstring model. Uh, and then those come into two types, type 0A and type 0B. So we've already handled the type 0B case for minimal superstring theory. And what we need to handle now is the type 0A case. There again, as I said, the matrix model is super easy. You can handle it. So it's the type 0A that we're working on in that context. And then the other project that we are working on is again in the category of superstring things, but instead of looking at non-perturbative contributions to all of this was about the vacuum uh, energy, roughly speaking. Uh, you can also look at contributions to scattering amplitudes that are non-perturbative, and they come from diagrams that involve like vertex operator insertions. So there again, it's sort of the set of words that I will use is it's the first subleading non-perturbative correction to scattering amplitudes in minimal superstring theory.
I
So
see.
there's a bunch of like puzzles there that one needs to resolve, and so part of the work we are doing is to resolve those issues.
So these minimal type 0A and type 0B that you're talking about, do they correspond to the, the well-known 10-dimensional type 0 and type 0B, which do have tachyons?
So these guys have tachyons in. So yeah, these are two-dimensional. The type 0A, type 0B just comes from like the GSO projection, which is also where
Mhm.
the type A and type B come from in 10-dimensional string theory.
Yes.
It's just everything again because it's two-dimensional is way easier to handle.
Hmm.
So yeah, it's essentially the same kind of GSO projection gives you these two types.
Right. So
Uh,
I asked this question because in 10 dimensions, when you make these theories, they are T-dual to each other. So
hmm.
can you have some similar relationship between them into two dimensions as well?
Yes, so dualities are well known between type 0A and type 0B two-dimensional theories. Uh, the simplest version where the minimal model is like a 2 comma 4, I think they're exactly related to each other. Like there's an exact duality relationship that at the level of the partition function is still very hard to see, but I think people have like theoretical arguments to show that it is the same. So you just change like uh, think probably corresponds to changing like 1 by GS to minus 1 over GS or something like that is
Hmm.
what does the full like duality transformation for you. But yes, there is a duality that takes you from 0A to 0B.
Right.
Um, but the instant on expansion looks very different in these two theories. So although the full answer after you've resummed using some Borel resummation techniques will look similar, the way these guys are expanded look very different, which
I
is why
see.
like the resolution for type 0A cannot just come from seeing that type 0B is resolved. There are sort of direct calculational pitfalls that one needs to handle to have like a direct resolution. Like I agree, maybe someone can argue that there's an indirect resolution through the type 0BT dual root, but what we're looking for is a more direct resolution where you match things directly one to one.
Sure, sure. I mean, even if there is a resolution using the T-duality map, there needs to be an independent check on these resolutions. So if
Yeah,
you
yeah,
can,
fair enough, fair enough.
right. Okay, so I do have some questions for you, which are regarding, the life of a person as a physicist, and then I have people's questions. I mean, I have more questions for you, but I have a lot of questions from the people when I announced this podcast, so I want to give
Yeah,
those questions more time.
okay.
So, before I go to the people's questions, I want to ask you that do you have any advice to, I mean, to be honest, I mean, you are a young researcher yourself, but people who are even, junior than you, do you want to give any advice to young PhD students, for example, that how to build um, collaborations during their PhD?
Yes, that's a great question. So, uh, I have found that most people in our community, at least, are sort of nice. And so, if you meet them at a conference and go attend their talks and go talk to them after, a lot of times, if that's something you're working on and there's someone who gives like a similar talk, go talk to them. That's how some of my collaboration started. Like as I mentioned with Andreas, what happened is he came and gave a talk. We started talking, and that's how our collaboration happened, basically, because I had some tools that sort of were useful for the kind of things he was doing. Uh, so that's sort of the easiest way. Most places you would have some, semi-regular seminar series which invite speakers to your institution for some kind of seminars, hopefully. So one thing you can do is go talk to your seminar speakers. Uh, the other thing you could try to do is if some interesting paper appears on archive, you can also try emailing people. So those are sort of the easiest ways to build collaborations. The third route is usually through your advisor. Your advisor can put you in touch with people that do similar work, and sometimes that can also lead to very fruitful collaborations. But
Right.
I would say, like, if you are a third year or higher in PhDs, try to build collaborations because that will be helpful as you start looking at the postdoc application process.
I see. Okay. So a lot of people, I mean, most, I would say all the people who, come to research, with the path of, bachelor's and master's,
Mhm.
they are very good at problem solving. They are very good at being students and doing their homeworks, and for example. So but a lot of people find it hard to do the transition from being a student to being a researcher. So
Mhm.
do you have any advice on how to do this transition? Because a lot of people who are very good at problem solving and doing their homeworks are not that good at being a researcher. Because for example, one of the big problems is that a homework may take like a month at most. It doesn't take more than that. But a
Yep.
research problem may take like years. And a lot of people get, this message from this big time frame that, okay, probably they're not good enough to do the problem and things like that. So this transition can be hard for a lot of people. So do you have any advice for younger people to, make this transition easily?
Mhm. So yeah, I think unlike a lot of fields, the challenge for a very mature and ripe field like hep theory is that uh, low-hanging fruit is already taken. So a big challenge for people in mature fields is to find a problem that is easy enough to be solvable, but also complex enough to be interesting. And so the big challenge of researchers in today's sort of hep theory landscape is to find problems that sit in this sweet spot.
Yeah.
Once you land upon a problem that has both of these features, the solution a bit, maybe after some amount of hard labor will come to you. But the main skill you're trying to learn after a certain point is the skill to find problems in this uh,
Yeah.
space of interesting but easy.
Yeah.
Uh,
I mean, it's easier said than done. I mean, it's very hard to
yeah,
find such problems.
yeah. I would say 90% of what you need to learn as a researcher is doing this. 10% is
Yes,
actually doing the calculation in my head.
I agree.
Uh, so, what will happen initially, and this is something I learned from collaborators usually, is you would start working on a project. And typically at the 1 or 2 month level, you understand, you start working on something new, you read papers, and after 1 or 2 or 3 months, you will realize whether there is this Goldilocks problem that exists in this particular direction or not. And a lot of times it is better to abandon something that doesn't seem to fall in the Goldilocks zone. So
Hmm.
not everything that starts will end up as a paper. I think this maturity and this understanding is extremely important because sometimes you can think of it as some kind of sunk cost. That, hey, look, I've been learning this for 3 months and it never turned into a paper. Some of it will come back to you later in your career, but sometimes, a lot of times, you will have to sort of painfully rip that part off, forget about it locally, start working on something new, and that is part and parcel of uh, the kind of landscape the field is living in today.
Hmm.
So that maturity is extremely important. Like you could be someone who can keep pushing at the project, but again, because you have a finite time, and you want to at the end of it, hopefully land up a postdoc or a professor position, you don't want to waste all of it just working on one problem, which might not even be solved in the duration of your current job or tenure or something, right?
Yeah.
So that is one thing that people need to understand is it's not a homework kind of thing. So at some point you might want to come back and reevaluate whether you have the tools, whether the problem is easy enough, because usually we start with things that are too interesting but not easy. Like you rarely end up with the other kind of problem where things are too easy but not interesting. Uh, so that maturity is part of what you're learning, especially as a late career PhD to early career postdoc position. Uh, that is my key advice. Like that is what you're learning. Part of what you're trying to learn is developing this skill of finding these problems. And it is again sort of full of failures of this sort where you will learn something and it will not turn into a project. So one thing that I would always recommend is at least have 2 to 3 projects in parallel if possible. So that even if progress on one is slow, you can sort of make progress on the other to keep feeling good about progress. And it's good to stagger them in the way that if one of them is sort of later in its sort of life, where you already have results and you're like working on sort of cleaning up and publication, those kinds of things, the other one can be in the early stages. So
Right.
that is one thing. And yeah, the second thing is abandoning projects when things don't look like they're moving forward. Uh, and in the long term, trying to develop the skill to find Goldilocks problems.
So you strengthen this answer by, referring to your own experience. So someone may ask that, okay, how many projects did you have to abandon?
Many. Uh, so yeah, I mean, including like maybe ones we are working on right now. So even this type 0 that I mentioned, we stopped working on it for a year, roughly speaking, because we realized it was too difficult and we didn't have the tools. And I
Mhm.
think we're sort of giving it a second go now. But if it doesn't turn out nice, we might again abandon it. So it keeps happening all the time. Sometimes after a little while, you realize, there's this new tool I could go and plug back in. Sometimes you sort of let them lie. Uh, there
Right.
are many other projects. I don't want to name them because then maybe someone else will
Sure.
solve them before me.
Sure.
So it's wasted effort. But there's like TTbar projects that we started, abandoned. Uh, Even with the first TTbar, it started off with a completely different problem where we were doing like non-symmetrical intervals in 2D. Realized that was too difficult, so let's do higher dimensions, but sort of somewhat symmetrical intervals. And uh,
Right. Right. Right.
so yeah, a lot of times, you might find some like jump, you might make like a horizontal jump that is a problem that is sort of interesting but solvable, that sometimes sort of saves a little bit of your effort, but a lot of times you just go in a direction and completely close off that direction locally.
Right. So when you say that you had to abandon these projects, you mean after working on them for several months, or
Yeah, yeah,
that
yeah,
you're
typically, yes. So yeah, I still have sort of overleaf or piles of notes from these projects, and if someone tomorrow comes and talks to me like, hey, look, I have something here, I can still revive them because they're still like living on a computer somewhere.
right, right, right. I see. So is it easier to start projects when you are at a place where you have a lot of postdocs, or is it the same level of difficulty no matter where you are?
I mean, having more people to talk to usually is very helpful because, everyone, especially like second, third year postdocs, starting then, people will have their own ideas. They will have their own project ideas. You can go talk to them, uh, especially for early career PhDs. They usually are just trying to find whatever they can land their hands on. So that's another advice I would give people is, too early in your career, don't say that I work on X or I work on Y. Uh, if you have like five different postdocs or two different professors who have somewhat different interests and you can collaborate with both of them and they work on things that have nothing to do with each other, just learn all the tools you can learn, at least initially. Like, don't close off too early, don't super specialize too early. uh,
Right. So do you think that it's if somebody gives this advice that um, you have to make your name in a particular field in your PhD to get a postdoc, so you disagree with that?
I would say I would disagree because I work with people at Berkeley who are doing more of these islands. I work with Raghu and folks who are doing more of these like super highbrow, computationally difficult, uh, minimal string theory kind of projects.
Hmm.
And on paper, they don't look like the kinds of things a single person would do, right? Like they just live very far apart in terms of skill sets, in terms of the kinds of questions. Uh, but I feel like they're nice because they give me a nice balance, right? Like on the one hand, I have things that are more sort of philosophical and more like proof of concept type papers. On
Yes.
the other hand, I have these like very calculational type papers, and they can sometimes make for a better sell for people when you can tell them like, uh, hey, look, I have both of these tools in my toolkit. So
Right, right, right.
it
So,
is good to have this diverse experiences, but that's true for me. Some people who have worked on a
Mhm.
single problem in the course of their PhDs and have like made substantial progress have also landed up very good postdocs. So I think it's again sort of what works best for you. Like if you're someone who like would concentrate on a problem and keep working at it for 5 years, 6 years, 7 years, no matter what, until you sort of get a breakthrough and you have an advisor who's supportive of that and you can get funding for that, go do it. And if it's a big enough problem, solving that problem will get you a postdoc. However, if you're someone who like likes the variety and
Hmm.
who likes some semblance of balance between calculation but also proof of concept, uh, uh, go do that. So my what has worked for me might not work for you, and so on. This sort of like multi-pronged approach is something that I like because I like calculations, but I also like sort of this new model building, new idea building kind of projects.
Right.
I
So
have
you
some,
think that,
go ahead.
uh-huh. No, no, you can continue.
I was just saying like I'm gravitating more towards the more mathematically sort of rigorous things because as you age, it's easier to keep doing the same thing for a longer time. You develop more tools. Uh, but initially maybe it's good to have both kinds of experiences, not just uh, for career, but also for you to realize which kind of thing you like more.
So what you're saying is that if your work is a bit scattered, it's not bad for your career. Because I'm asking that question because some people have given me that advice that if your work is scattered, it's bad for your career in your PhD.
I don't think that is true. Uh, as long as like maybe also depends on the level of scatter, but I don't think that is true. I feel like even if you have a couple of collaborations with condensed matter people where you've done more like numerical computations for CFTs, even that can be valuable to some people in hip theory. So again, different people like to hire different kinds of postdocs. So sometimes what you will find is people whose work is diverse will hire postdocs whose work is also diverse. Like my
Mhm.
PI right now, Vijay, his work is super diverse. He sort of works all the way up to neuroscience. You can find him like writing a bunch of papers there, right? So he likes these diverse kind of people. So some other people might hire postdocs who are also more restrictive. Uh, but given the nature of the field, uh, because again, it is very difficult sometimes to keep working in a single direction. And there's also like a diminishing marginal returns to working in the same direction because if you publish like 5 papers, does the fifth paper really have that much increment over the fourth paper? Sometimes diversity can help. So yeah, if all of those 5 papers are super high quality, maybe same line of research is great, but a lot of times quality also declines. As you keep
Yes.
exploring the same direction of research, you might like, just make incremental progress. Like uh, for that reason, I would say like diversity is not bad. Uh,
Hmm.
and there will be people who would sort of appreciate your diverse experiences in hiring postdocs.
Hmm. Although you are still quite young, but in your experience, do you think that number of papers determine whether you will get a postdoc or not?
I think there's probably some semblance of a cutoff. Like you probably want like at least 3 or 4 papers if they're like
Hmm.
reasonable length in the sense of like 40 to 60 page papers. Uh, Maybe at least 3 or 4 is expected. It is possible that you have a single great result that challenges everything that we've known about the field, and it's like a 300-page tome really that could get you a postdoc. That's typical. That's very atypical. So I would say for most people, like they're writing sort of the standard length papers between 40 and 60 pages or 30 and 60 pages, and I would say at least like 3 or 4 is a reasonable cutoff. They're expecting at least for late career PhDs that they're publishing at least about 2 papers a year. So at least, in your like last 2 years, you might be expected to publish 3 to 4 papers, even if you've not done anything in the first 3 years.
I see. Okay. So one more question is that, wait, I think I have asked that question. Okay, yeah, I think I've asked that question. So let me go to people's questions now. And I have quite a lot of people's questions.
Mhm.
So some of these questions may be vague, but you can, I mean, we can try to make them as precise and specific as we want. So the first question is that how was transition from JEE minded to doing a PhD in physics was like? How much his time in doing graduate level problems increased as compared to his JEE questions? How is the postdoc? I mean, there are a lot of questions in this question, but I think you can ask answer the first questions, first two questions actually.
Okay, so sorry, what has changed between my JE time and my.
So how much is well, I think the question just says this: how much is time in doing graduate level problems increased as compared? I think the question is trying to ask that is the time required to do graduate level problems significantly higher than doing JEE level problems? I think that's
I would
the
agree because JEE you're expected to solve about 20, 60, 70 questions in 3 hours. So you'll spend like 3 minutes a question. if I solve a graduate level problem in 3 minutes, like maybe I'm a genius or something. So yes, the time is substantially changed between like 3 minute to for a paper, you might work on a problem for 3, 4 months. So that is how much it has changed in terms of uh, timing, and that's partly, as we discussed, to do with the kind of problems you have. Like exam problems, homework problems typically tend to have a solution. It's a known solution. If you do the steps in a particular order, you're going to get the solution right. Research is fundamentally different. A, you don't even know what's the right approach. B, you don't even know if the solution is going to be found. So that's how the timing sort of changes. Hopefully that answers that question.
Right. So the next question is, I mean, it's a very general question. So if you want to
Mhm.
say something about it, you can. So the question is that, what is the current state of string theory?
Uh, from my very limited perspective, it looks like we are making great progress.
Mm-hmm.
Uh, Islands was sort of one of the, I'm not sure if people now think of it even as string theory, but Islands was like a very interesting and important result. And that's brought us much closer to resolving the information paradox. So that has been very interesting. Right now, people have used these tools from math like von Neumann algebras to understand how uh, things work in the world of holography, and that has been very fruitful. So I think the community as a whole is thriving. Uh, there's a lot of connection with math that people have made over the years. So mathematical physics is also been very fruitful. If it's a question about experiment, I do think we've steered a far ways from what experiment can achieve. I don't necessarily think it's a really bad thing. I think we're making sort of great progress, but if it's an experimentally minded question, I don't think experimentalists would catch up to what we're doing for like maybe a decade at least, or maybe longer. So it,
Right.
it
Okay.
has turned into a very like theoretical discipline, but I think it's sort of thriving. It's doing really well, and people are making great progress.
So the next question is that how to stay always dedicated in physics research from class 12th rather than distracting in other areas in life and society.
Uh, Again, so maybe let me like, A, do I even believe in the philosophy of the question? I'm not sure I believe like that you should
Mm,
just keep doing physics because again, it's hard and challenging. And one thing that's again helped people during their PhDs is having something outside of physics sometimes can be helpful. Something that you can, sort of use in times when problem solving isn't going the best. Having some place of excitement can help you sort of keep motivated and not sort of get anxious or stressed or depressed. Uh, so that is one thing I would recommend is don't do all physics. Maybe like at least have a couple of hours, achieve some semblance of work-life balance. It is very hard for a PhD student to do that sometimes, but I would sort of advise in favor of it because that helps you get through tough times. On the other hand, there are sort of maybe things that are not the most productive. Uh, a lot of uh, things like maybe digital media have gotten very good at grabbing our attentions, and that can have a detrimental effect on both your mindset and on your time. So avoiding them might be a good idea, but don't give up like social interaction. Don't give up like if you play a sport, go play a sport. If you like doing other things in your like leisure time, go do some of that. Uh, yeah, that's sort of my simple advice.
I see. So the next question is that what are the things that you considered while selecting the PhD position to accept?
A couple of things like, okay, so the obvious academic things would be, choice of advisors. If you have the option, my suggestion is choose a place that have more than one people working on the field that you're working in, because if that one person doesn't click, you sometimes need that other option. The other thing, uh, which might not be easy for everyone to figure out, but you want to figure out by a certain point in your PhD whether you prefer a hands-on or a hands-off advisor. That can be very helpful because I initially wanted a very hands-on advisor. So I met with my advisor thrice a week initially, which is unheard of for like some people. But that was kind of the working style that I preferred, at least initially. And I found that to be very helpful. So that was a factor that contributed. Um, the other thing that I also chose my place on was sort of the kind of community that the school provides. So I wanted to go to a school that has some semblance of community and people who were like, a couple of years older than me, like third year, fourth year PhDs. You usually go talk to them when there's like an open house day for your visit, uh, and making sure that those people are doing well, that those people are happy, that people are getting postdocs out of the institution can be good indicators as well. So that's another thing I would recommend doing. And that's probably the strongest indicator you want to do is go talk to people who are in their third, fourth, fifth years. Uh, Check if they're happy, check if they're making good progress, check if they're getting like postdocs, if they're sort of at that stage of life. Uh, because you will most likely be one of those people, right? Like in a couple of years. So that is the key piece of advice. Like most people will focus on the professors when they're going for open house, but I would say focus on the grad students and see if they're doing well. Because even if the professor is like a hot shot, it is possible that maybe that person's advising style might not work for you or something else. But if the students are happy, you're more likely to be happy there.
I see. Okay. So the next question is that were there times when you felt you were not motivated to study physics?
Uh, Probably yes. Although like maybe physics broadly is very hard to say yes to, but like there are times when I'm doing a particular project and I don't feel like doing that, and I might switch to some other project I'm doing. Or if I have two projects and both of them I'm like not particularly interested in for a week or a couple of weeks, I might sort of, go low on research and spend that time doing something that energizes me. Uh, but I have sort of again over time developed the skill to like not have a single rough patch because again those projects now in my head are compartmentalized differently. So
Hmm.
if there are three projects, there might be a time when I'm not doing project A because I'm not motivated on that one, but maybe I'm doing B or C. So physics more broadly now those times are rarer, just because in my head they are sort of there's no thing is physics. There's project A, there's project B, there's project C.
I
uh,
see. So the next question is that for those interested in theoretical physics academia, do you think it is easy to be financially secure in case they do not end up getting a tenure track position like going from postdoc to industry?
uh, So if I look at sort of data around me, a lot of people like switch into industry. The common things have been like either things like fintech or more recently have been like AI research. Those people are, I mean, the joke is that the moment these people graduate and move to their jobs, they're making more money than their advisors have after a full career.
Yeah.
So yes, if you want to make that transition, it is not unheard of. A lot of people around you will make that transition. The field going from PhD to postdoc has a good attrition rate, which means like uh, maybe 30-40% of your peers will leave the field and do something else. And most of those people will probably end up in the industry. So during a PhD, your salary won't be super high. But if you are motivated by monetary concerns, or if you just want to leave academia for some other reason, it is not incredibly difficult to get a job that pays you well, especially if you can brush up on things like coding and maybe AI. Like you'll probably have to spend like, 3, 4, 5 months, maybe a year at most, uh, learning some of the tools that will get you through the interview process. But a lot of people, even in their last years of PhDs, will do an internship at like a hedge fund or a fintech company or AI company. And if that appeals to them more than academia, they will make the transition. And people do it at the level of PhDs, they might do it at the level of postdocs. I've even like interacted with people who were tenure track faculty, didn't get tenure, and then make the switch. So
Yeah. That internship thing, I think if you are a PhD student in the US, then you can't do internships. Then you have to just learn it on your own, right? because the visa
Uh,
regulations don't allow you.
but you can do a OPT, right? Like summer
Oh,
OPT.
okay. I
Yeah,
see.
yeah,
But that
yeah.
happens after the PhD.
Uh, so there's CPT and there's OPT. So one of them you can do
Yes,
during your
okay.
PhD, right? So even
Right,
for
CPT is included.
internationals, even as internationals, like for a summer, you could do a summer CPT or something, I think.
Yes. Okay, I think yeah, that's what you're talking about.
Yeah.
Okay. So this next, I don't know how to, what this next question is
Yeah.
trying
Sorry.
to ask,
Just
but
getting back
yes,
there.
sorry.
The CPT is not the biggest issue. The biggest issue might be convincing your advisor to let you do an internship. The technical
Yes.
logistics aren't that bad because, like, even as undergrads, a lot of people do internships on CPTs, and you can do exactly the same thing as a graduate student. Like the laws aren't any different.
Okay, I see. So the next question, I mean, these are the exact words of the question. I
Yeah.
don't know what
Yeah, yeah, I
what to make of
understand.
this.
I've heard it.
So what I don't know what to make of this question. But the question is that, do you have any advice for not so smart grad students starting theoretical physics?
Uh, I'm not sure what you mean by not so smart because what's going to happen
Hmm.
in the course of your PhD is that at the end, you will be an expert in something. You will be the expert in the papers you've written, and you will, in that paper, be the smartest person in some sense. Uh,
Hmm.
if you work in a particular field and you've been doing that for 4 or 5 years, you will end up being the sort of world expert in that field just by the virtue of having the most experience and knowledge and calculational ability in that field. Uh,
Hmm.
if if what not smart means is sort of the skill or the knack to solve calculational problems, then my suggestion would be, reconsider. Like if you feel like I feel like I'm not cut out from the cloth that makes good coders. It is not a smartness problem that I cannot code well. It is like it's an ability problem or it's a motivation or a mindset problem there. So my suggestion for those people is if you feel like you're not smart because you cannot learn the kind of skills that are needed to be a hep theorist, maybe that's telling you that you shouldn't be one because uh, different fields require different kinds of ability. And maybe if you enjoy the experience of writing code more or debugging an experiment more, why are you even trying to be a hep theorist? Like, there are other fields that are equally great. Just make the switch. So it's not a smartness problem. It's more of a what do I enjoy doing and what do I have a skill set in doing kind of problem. So that is my basic advice is like you don't like not everyone has to do hep theory. It's if you do condensed matter experiment, it's not at the end of the world. Those people do incredible research. Those people write great papers. So like reevaluate. Uh, Sometimes you wanted to do hep theory because you were motivated by reading a book, but once you enter the field, you realize it's not your calling. And then at that point, like just don't sort of keep hitting against the wall. Just reevaluate and change advisors. And I think at least in the US, most schools, people would switch advisors, even third year, fourth year PhDs would switch advisors at times if they don't feel the field is right for them. And I think that is a reasonable thing to do if you realize that. It is easier to do in a first or second year setting, uh, but it's not unheard of even for people in their fourth years to switch advisors.
I see. So the next question is that in his journey towards theoretical physics, there must have been a lot of ups and downs, I guess, that he would have faced. What's his advice for someone who is passionate about physics and going through these ups and downs?
Again, sort of maybe ties back to older questions. Like if you have multiple projects, the downs in ones can hopefully be counteracted by the ups or moderates in the other. And so you can
Mhm.
focus your energy on things that are going well. If both of your projects or all three of your projects don't go well, have a little bit on the side that can keep you going, at least through the rough patches. Uh, the other thing is sort of building a support network. A lot of times those might be, your peers at your graduate school or undergraduate institution. It could be sort of family. It could be a network of advisors maybe that can help you out. Uh, Postdocs, having a support system that can sort of help you get through tough times can also be very, very helpful. So uh,
Mhm.
those are my key pieces of advice are try to have like a little bit of a diversity in what you're doing at any moment so that the downs in one can hopefully be counteracted by the ups in the other.
Okay, so this next question that came from the people, actually, I have asked this question to some senior academics as well, and
Mhm.
most people say Jackson electrodynamics. I mean, only one person said Hawking and Ellis. So the question is that, according to him, what's the most challenging textbook that he ever read?
Mm. So I really like electrodynamics. Like I feel like if there was research left to do in classical electrodynamics, I would love to do it, but I think like a lot of it is done. So
Mhm.
I think Jackson is a difficult textbook, but I also enjoyed reading Jackson just because I like sort of electrodynamics a lot.
Mhm.
Uh, Maybe the hardest textbook I ever read might be something I was never interested in. So it could be a computer science textbook I read at some point, like I sort of absolutely dreaded the experience of reading it. It's rarely when I'm reading a physics textbook that I dread the experience. It's either like physics, either some kind of like, some CS textbook or some like organic chemistry textbook or something, which I had to read for some
Mhm.
course. Talking about maybe pure physics, uh, I really don't have a good answer, I feel like.
Okay, it's okay. It's fine. So the next question is that what are the bare minimum courses an MSc graduate must have under his or her belt, apart from the core courses, to at least begin graduate studies in the areas that you work on?
So I would say like at least advanced level QFT, if you're like a master's student, you should have some advanced level QFT under your belt. If your institution offers string theory courses, those would also be really nice to have. In addition to that, uh, yeah, I think a lot of it, again, the gap between what a course is going to teach you and what you need for research is so large that after learning the basics from a textbook or a course, you will have to read a lot of papers to actually learn stuff. So
Mm-hmm.
I don't think like taking 5 courses in string theory will teach you everything you need to know to do research. Uh, so a lot of it is not really courses, but it's more like doing research or attending seminars or attending talks that's going to help. When you start attending seminars as like a first year student, you don't understand like 5% of it. That is fine. That is expected. The seminar is typically not intended for people who are not experts. But it's important to go to those seminars so that you sort of hear the jargon and you at least understand, first 5-10 minutes initially. And if something really interests you, you can go look at the papers again, read the papers, read some of the references or review articles that are cited in the papers. So I think at some point the education is going to shift from a course-focused education to a more research-focused education. And so even people who have like advanced level QFT in their coursework are somewhat ready to start working on things like these CFT things I've discussed. They will take at least 6 or 7 months of reading a CFT textbook to get to the point that they can start contributing. But there's typically no courses that will teach you that, anyways, by the virtue of
Right.
the fact that maybe at your institution you're the only person who's interested in CFT. There's no like point running a course for two people. Courses are typically run for like big audiences. And so the QFT course you will take will have Hep theorists, phenomenologists, experimentalists, AMO physicists, is trying to cater to all of them. After a certain point, the courses will start losing relevance to what you want to do as a researcher. So I would say advanced QFT plus sort of string theory courses is the best you will get. And after that, it's sort of all the things you can learn on your own through textbooks, papers, seminars, yeah, podcasts.
Yeah, sure. Okay, so the next question is that have you ever struggled with social media addiction?
Uh, so the good thing was when I was sort of high school, early undergrad, there wasn't that much social media that was available to us. Like we didn't have
Mhm.
sort of particularly sophisticated smartphones. Uh, Even currently, I feel like I don't have a presence on most social media. Maybe that's not really the best thing. Maybe I should do a little bit more. I don't know, maybe to just advertise my research, but I don't have a sort of presence on any significant social media.
Right.
Um,
I think when people mostly say social media addiction, they also include YouTube addiction, which is not exactly social media addiction, but it's an
Right.
addiction.
So that might be the only thing I do. And they're also like, I might watch a lot of long form content. What I sort of
Hmm.
have tried to sort of avoid as much as possible is like short form content, because it's very scrolling friendly and you can sort of waste a lot of time doing that. You could do it, if you're commuting or for like 10 minutes, 20 minutes, if you're like stuck in some boring place. I would recommend avoiding it because they're extremely addictive by the virtue of the way these algorithms are designed. They will
Hmm.
keep you stuck in a loop. Uh, so one advice I give if you're really stuck here is like stop doing YouTube on your phone, like do it on your laptop. That makes like watching shorts a little bit harder, at least. There's like a little
Yes.
bit of a barrier to doing that. And then for the other things, I avoid it. But that's probably because I can live this hermit's life. Maybe you cannot, and you need to be connected. And so turning off like notifications can help a lot of people. Uh, Maybe partitioning time away can help people. Uh, Switching from a laptop, switching to a laptop from a phone can help people. So those are sort of some things one can do. Yeah.
So a follow-up question: have you ever, felt that watching YouTube videos are watching YouTube videos is affecting your attention span?
I think I have, again, so as I said, like I try to avoid short form content because I feel like that sort of hits my attention span the worst.
Mm-hmm.
Uh, the other thing is I've sort of been very lucky to have always had the ability to keep doing the same thing with a lot of concentration as a kid. So I was never a multitasker. I was always like a unitasker. I can only do one thing at a time.
Mm-hmm.
So luckily, my concentration hasn't eroded too much over the years. And even if I sit down to a calculation today, I might like, spend all like until 5 a.m. in the morning, like if I'm stuck in a calculation. I am very happy to like not sleep until 5 a.m. because I'm just stuck there. I can't even like unplug and sleep sometimes. Uh,
Sure.
so I partly because of like biology, maybe genetics, maybe social conditioning, have never struggled with these things. And I have like carried forward some of those skills into like my current life. But again, this is not something you can like develop on the get-go. Like you can't just be like, hey, look, I'm not going to, if I have the attention span of 5 minutes, I'm going to make it 5 hours today. That's not going to happen. You can probably develop those skills over time. I have luckily never had to struggle with it, so I have no advice for how to do it.
Sure. Okay. So the next question is that I am preparing from I'm preparing for IASC as he is a International Physics Olympiad gold medalist. What advice would he give for preparing? Sorry, it says that what advice will he give to someone who is preparing for International Physics Olympiad? Yeah, I think that's the question. Yeah.
Okay, so for IFO, I think there's a multi-staged exam, and the advice will depend on what stage of the exam you're in. So I think for the first two stages, roughly, they're expecting like advanced problem solving ability in the kind of high school physics that you do. So my recommendation is like just solve advanced level problems using like maybe textbooks you use even for like a JEE preparation course, for instance. Things like Etsy Verma and uh, Irodov, I think is especially good there because it's a lot of
Mhm.
mathematical problem solving. And the other thing you should do, certainly do, is like if you can get your hands on the past 10 or 20 years of IFO exam papers, just try to solve them, especially in the later half of your preparation. And if you're performing reasonably well on them, then your preparation is good. So uh, IFO, especially the exams, are a lot of mathematical problem solving, especially for the first few stages. So having a good handle on mathematical physics, not in the sense of like modern research mathematical physics, but like using math to solve physics problems is really helpful. And yeah, textbooks and preparatory material is probably your best bet.
Okay, so the next question, and I think this is the second last question. So the question is that if someone wants to go to academia to do physics research, but family gives him pressure to do engineering. What will be his advice for someone who is in this situation?
So again, I think there's like a lot of different things that one needs to decide on here. Like one of them is like, what's the financial condition? Because, if you're a PhD student, we don't get paid too much.
Mm,
If your family is expecting you to start earning money, your best bet is probably to get some kind of engineering degree and start like uh, working as soon as you graduate. Uh, so my advice would be like you should, before you jump into something, like make sure that your financials are appropriate. Like most PhD students can sustain themselves. I don't think they can sustain like a family expenditure if your parents are expecting money or if your
mhm.
significant other is expecting money or your kids are expecting money out of you. That's not going to work for most people. So be mindful of the economic circumstances, of the potentially like social circumstances. Maybe there is a reason like you cannot move to the US to do an undergraduate degree because there are some family issues uh, potentially. Uh, so be mindful. The other thing is, even if you start in engineering, there are like disciplines that live on the intersection. So, like IIT Bombay runs the engineering physics course, which is part engineering, sort of part physics. And people from there can make it into a theoretical physicist, but people from there can also make it into more engineering centric careers. So sometimes, reaching a compromise can be helpful. Uh, so it's really dependent on your circumstances, uh, your situation. Uh, so I don't have like a one size fit all advice for everyone, but if you have the means for it, maybe try to convince your parents. A lot of times, again, as I said, people make the switch uh, a little bit later on. Like maybe you can make a switch from engineering physics to more standard physics, uh, or you can make the switch later. Some people might make the switch by starting a master's in something that is more engineering physics, uh, somewhere in the middle of that, and then in their PhDs make the transition fully. So you can start out in electrical engineering and then do some like, quantum optics for your master's and then like go into full-blown like AMO physics uh, in your PhD. So that could be another route where you start in a very engineering heavy discipline and make your way to physics if uh, that is what you want to do. But if you don't want to do that, then after maybe electrical engineering, you can just make it into a more standard engineering career. So there are many ways that can lead you back to physics.
You use this acronym. I'm not familiar with this acronym. What do you mean by AMO physics?
Atomic, molecular, and optical physics.
Oh, okay, I
Yeah,
see, I see.
yeah.
So the last question from the people is that could you ask him how should a master student with a background in QFT and GR approach a physicist working on string theory or holography in a different institute for research or thesis? Is it by reading their papers or is there something else?
Yeah, typically reading papers will usually be very advanced if you have no experience in that area. So I
Mhm.
would say like if it's CFT, like go read the big yellow book or something. If it's some other area, go read a textbook because those are written for people who don't know much about the field. So start with textbook, review papers, and then like actual research papers. If you directly read a research paper, you might like understand very little of it. So gradually build up to it. And once you feel confident with sort of uh, the kinds of questions that you have, uh, you can do that. Sometimes if you read a paper, people are very happy to answer questions. So even if you cold email them asking, hey, look, I read this paper and this is something I don't understand, I would say like 40-50% of the people you write this kind of email to will respond to your emails. And that can also serve as a conversation starter with a lot of researchers at other places.
I think, sorry, this is the last question. The question is that if you are applying for a postdoc, is the number of papers more relevant than the, wait, what does it say? Yeah, than the reference letters that you will receive.
I would say like most people start reading from the reference letters. So typical advice is that those might be the most important pieces of your application, but it varies from reader to reader and institution to institution.
Mhm.
I have not been a professor, as you can tell, so I don't know how these people make those
Mhm.
selections. So if you have more senior people on your podcast, maybe they can better answer.
Sure.
But my understanding is uh, most people will like look at who your reference letter writers are, and if they've never heard the names before, it is probably because they don't work in a similar field.
Mm-hmm.
And those people will like then maybe not start reading your application any further just because, I mean, I pretty much know everyone's name whose research I'm interested in, right?
Mm-hmm.
And that would be the first segue into how these people will read your application is from like points of contact that these people have knowledge of. And those points of contact are obviously either papers or letter writers or collaborators. So it's some combination of both things. And like if you have three letter writers, it is expected that you would at least have papers with two of them. So some of these letter writers also turned into collaborators and also turned into papers. So
Mm-hmm.
it is very rare that you will get a strong letter from someone who you've like talked to once in your life.
Yes, true.
Typically, your best letters would come from people who are collaborators. So it's
Yes.
not that disentangled, right? The fact that you have a letter writer is usually not that disentangled from the fact that you have a paper.
Sure, sure, sure.
Yeah.
Okay, so I think my questions are over. Thank you so much for your time, and I hope
Mhm.
that sometime in the future we can also, talk about something as well,
Yeah,
about your
of
work.
course. Yeah, I really enjoyed the podcast, and hopefully the viewers enjoy it too.
Sure, I'm pretty sure they will. So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.